Study of bimetallic nanoparticles obtained by ion irradiation of synthetic sapphire substrates. Cancun, Mexico, August 2023. Materials at the nanometric scale are well known for presenting new and exciting properties that may differ enormously from the properties in bulk. Metallic nanoparticles, in particular, possess a significant absorption band due to the conduction electrons' collective motion, the so-called local surface plasmon resonance. This band appears in the near UV or visible region of the electromagnetic spectrum. Metallic nanoparticles have also been widely investigated for their catalytic properties. A system of particular interest is the silver-platinum 1. A large miscibility gap characterizes this system, and the silver-15 platinum-17 phase has only been recently identified. We have found that this phase shows no significant local surface plasmon resonance, despite the large amount of silver contained. A low-angle reflection characterizes its X-ray diffractogram. A first series of pristine substrates were initially implanted with 1.5 megaelectronvolt platinum ions. After that, the sample was annealed for 120 minutes at 1000 Celsius degrees to promote the formation of platinum seeds and their growth. 0.85 MeV silver ions were implanted afterwards, and second annealing at degrees Celsius was carried out for 60 minutes. The Rutherford backscattering analysis confirmed that both ion distributions overlapped at a projected range of 200 nanometers. Scanning electron microscopy confirmed the formation of nanospheres with radii distributed around 3 nanometers. The resulting nanoparticles showed a clear local surface plasmon resonance at the wavelength corresponding to pure silver. Compared with simulations by the Mie theory, one finds that this optical response agrees with a core shell structure with the silver atoms at the shell, which is also thermodynamically favored by its lower surface energy. X-ray diffraction shows that the lattices are very deformed and that a broad region of solid solution must extend across the border. In this example, the reflection corresponding to the 311 plane is located above the silver 1 and below the platinums. Silver ions were initially implanted into a second set of pristine samples, and without any annealing, platinum ions were then implanted. Final annealing promoted the silver-platinum nanoparticles. Rutherford's backscattering again confirmed that the two ion distributions overlap without long-range diffusion. Scanning electron microscopy confirmed the existence of nanospheres, as in the previous case. We chose this sequence for this set of samples to inhibit the formation of nucleation seeds so that it would take place simultaneously for both kinds of ions. The optical absorption spectrum of this example at the end shows no significant surface plasmon resonance, but only a broadband corresponding to a few remnant silver nanoclusters. Exclusively for comparison, a spectrum of pure silver nanoparticles with its characteristic pronounced surface plasmon resonance is also included in this graphic. The reflection that appears in the X-ray diffraction at 19 degrees, corresponding to the huge interplanar distance of 4.5 angstroms, confirms that the silver-15 platinum-17 phases predominate the crystalline structure of these nanoparticles. Those planes correspond to intercalated silver and platinum planes in the lattice structure of this phase. In conclusion, we can affirm that by implanting first point ions, then annealing to promote the formation of PT seeds, then implanting ag ions and finally annealing again, one obtains PT ag core shell nanoparticles with a prominent silver surface plasmon resonance and broad reflections in its diffractogram that correspond to ag and point planes and to those of their solid solutions. On the other hand, when one reverses the implantation sequence and performs no intermediate annealing, the silver-15 platinum-17 phase in the nanoparticles dominates, and the absorption spectrum exhibits no significant plasmon resonance. At the same time, the X-ray diffractogram shows a reflection of the large interplanar distance present in this phase. This silver-15 platinum-17 phase has only been observed in nanodomains, as in the case of the nanoparticles reported here. Combining and optimizing the previous structures by varying intermediate implantation and annealing parameters is possible. The authors thank Diego Quiterio Vargas and Samuel Tawacanero Cuapa for their valuable help in the Central de Microscopy facilities, and Antonio Moreno Espino and Alejandro Herrera for the XRD measurements.